Okay, off we go. So, real quick reminder, don't forget about the attendance quiz. Code, Canvas, got a minute and a half left. Okay, so where we were last time, we were talking about the fundamental theorem of calculus, not because I don't think you know the fundamental. I know y'all know the fundamental theorem of calculus. The purpose of this is to point out how it's, in fact, one of our accumulation theorems that we've been developing, right? So we have this idea of an accumulating quantity, the whole is the sum of the parts, and we've pointed out that whenever you have an accumulating quantity, there is an associated notion of stuff. You can view it as a stuff distributed over the interior of the domain. And then that means that there is some sort of associated density, and you can integrate densities to get theorems. Okay, so in fact, the fundamental theorem of calculus fits all of this, right? Because change is an accumulating quantity. The whole is the sum of the parts. If you know how much something changes over one interval, and if you know how much it changes over a subsequent interval, put them together, the total change is the sum of those individual pieces of change. So it's an accumulating quantity. It's a little bit weird to think of it this way, but change is a kind of a stuff. You can think of it like stuff. It isn't actually, right? But you can think of it that way, and it's very helpful in various senses. So the whole is the sum of the parts. We have an associated density. We can ask, what is this associated density? What is the thing that you multiply by input change to get output change? Oh, right, yeah. Oh, that's the derivative, right? We know that that's the derivative from way back, right? And then I can kind of reinterpret this idea of the derivative. And this is where things get a little bit strange. I'm going to suggest now that, not that you have to, right? But that it's very helpful, very instructive to add to your list of perspectives on the derivative. Now, most students' primary point of view on the derivative is that it's a slope of a tangent line. Okay, yeah, it is. If you're looking at a graph, which it may or may not be, but that's a nice point of view, rise over the run, fine, cool. In a different context, you can think of the derivative as being like a velocity. Well, that only makes sense if you're viewing the function as representing position, right? Not height, but representing position. Then the derivative is velocity. Yeah, sure, cool. That's a nice point of view too. Third point of view, much more useful in this context, is to think of the derivative as being a density. I know it's strange, right? But I mean, you kind of got to give it to me that, look, if we think about the derivative as, the rise over the run, right? We think of it as being, blue divided by green. Okay, well, rise over the, if you're looking at the graph, etc. But think of the rise as being how much stuff are we talking about in a little subinterval. I mean, after all, it's a change. Change in the value of the function is a kind of a stuff. We're thinking of it as stuff. And it's the stuff per unit. Now, again, you can think of the green part down here as being input change, but it's also the size of a piece of the domain. So, yes, it's rise over run, but also it's stuff per unit size, and that is a density, right? So weird, strange, but familiar, right? Stuff per unit size, we've talked about that as a notion of density. Accumulating quantity per unit size is an integrand. It's the integrand and a density. It's just like Green's theorem. It's just like Green's theorem. It's just a different kind of stuff. Accumulating over a different kind of a domain, now an interval instead of a area, right? But totally analogous. Okay, so that's kind of nice, and I do think it's a useful point of view. It kind of adds to our list of theorems that we have successfully taken the point of view of as being accumulation theorems. So we talked about Green's theorem. We talked about the two-dimensional divergence theorem. Both of these theorems talking about different kinds of accumulating quantities. resulting in different theorems, but they're all kind of the whole of the sum of the parts, etc. Right? Now, fundamental theorem of calculus. It's our third accumulation theorem, and there will be several more. Right? Okay. All right. So, aside from adding to our list of successes in this line of reasoning, there's two more really nice things about this. Now, I've made some difficult requests of y'all. I have asked y'all to take the point of view that a circulation that's computed around a boundary curve, to think of that as stuff happening on the interior. And that is weird. I mean, how am I supposed to understand? I mean, if it's computed on the boundary, what do you mean it's happening in the interior? It's a weird ask. I fully grant that. This is going to help with that ask. So how so? I mean, how's this going to help with that? Well, because this is already an example where something that's computed on the boundary, right? If you want to talk about how much change we have, we look at the boundary points and we look and see literally, f of b minus f of a. It's computed on the boundary. I don't have to look in the interior if I don't want to. I can just say, you know what? Look at those boundary points. That's how you compute change. It's a boundary thing. But is it really? Where is the change actually happening? Is the change happening at the boundary? Nonsense. Look at this. This is where the change is actually happening. You can see it right there in the graph. Right? That's where the change is actually happening. In the interior of the interval. Right? So this idea that something that's computed on the boundary, that you should think of it as happening in the interior, well, of course you should. At least in this case, right? I mean, not a weird ask here. That's, of course, what change looks like. So when we go back to thinking about Green's, when you go back to thinking about Green's theorem and this weird suggestion that circulation is actually somehow happening in the interior, it's just a sort of a different example of what is perfectly intuitive right here. Okay, so I think that's a tremendous value of thinking about the fundamental theorem from this accumulation point of view. It gives you some sort of reasonable, hopefully satisfaction of this weird idea about circulation accumulating over the interior. The other thing I like about this, the integrand, the density. The operator, the formula that makes the theorem work, that integrand points directly to where that stuff is in the interior. It tells you how much of that stuff there is in any given sort of general vicinity. So, for example, let's look at a point like this one. At a point like that, okay, well, the derivative is large. Right? Substantial anyway. I mean, not huge. It looks like it's about 1. But the point is, it's a substantial derivative. And yeah, that's telling you how, yes, the function is changing pretty significantly there. And you can see it right there on the graph. Over here, where the slope is, it's still positive, but it's clearly smaller. Yeah, not as much change happening there. Right? And then back over to a point like this, where the derivative, let's assume my drawing is to be taken as given. Derivative appears to be 0 there. Yeah, no change is happening there, right? So the derivative literally tells you how much of the accumulating quantity, in this case change, how much of that accumulating quantity is happening where in the interior. So nice interpretation of, how to think about these integrands, and we can quantify that. I mean, this is going to look like a silly example, but we've got a total amount of change of 9. Obviously, that change happens in the interior. You can see as you progress along the interior, you can see the change happening in the interior. It doesn't happen at the point 0. It doesn't happen at the point 3. Right? It happens in the interior. So between these two candidates, 1 and 2, where is there more change happening? Well, if you want to know where the change is happening, you look at the change density. You want to know where something is, the density tells you how much of what you're looking for is where. Okay, well, there's the formula for the change density, aka the derivative, old news. Y'all know how to plug and chug. You can compute those. And more of it, apparently, 4 being bigger than 2, right? More of it is happening here at 2 as opposed to 1. And again, totally satisfying. You can see it right there in the graph. There's clearly more change happening at 2. And so as predicted, the derivative is telling us where the accumulating quantity is. So, okay, so now reminder. We have this idea that the, sort of geometrically, the density is telling us where and how much the change is happening in the interior. And then we can quantify it by looking at the actual explicit formula for the change density. So let's do the same thing now. Again, keep in mind the whole point of all this fundamental theorem stuff. The whole point is to serve as kind of a launching pad, an analogy, something to compare and contrast with the bigger theorems we're doing now, like Green's theorem. Right? So let's play the same game now with Green's theorem. Can I see geometrically in a picture, let's say kind of like this one, that the circulation that I compute on the boundary is actually happening in the interior, and can I kind of geometrically tell where? And yeah, totally. Because circulation, here's how you compute circulation. We literally do line integrals around the boundary. That's how we compute boundary circulation. It's measured on that boundary. I suggest that we can think of this as being something that's accumulating over the interior. And where is it? Well, I claim it's in this gray region. Now I'm going to try to zoom. I have to get the stylus for there. Okay, here. Ooh. Okay, let me try to get all this on the screen. That's going to be good enough. I think I can do that. Here we go. Claim it's happening in the interior. And let's think, for example, about some little square like that. I claim that a significant amount of this purple circulation is actually coming from that little green square. And I can even geometrically point to how much of that circulation is coming from that green square, because we can straight up compute the circulation around that green square. And you're going to notice that as I go along this part, right, or along that sort of bottom edge of the square, and you notice that the vector field is going that same direction on that sort of light blue edge of the square, we're going to have a significant amount of vector line integral there. The fluid is literally flowing along the curve. That's what vector line integrals look like in the context of fluids. The fluid is literally flowing along the curve. Let's see here in on this edge, the fluid is not flowing along the curve at all. The fluid is flowing perpendicular to the curve, so 0 there. By the way, also 0 here. Not flowing along the curve at all on that edge. But now let's think about this top edge. On the top edge, the fluid is, it's kind of flowing. It's along the curve, but in exactly the wrong direction. It's backwards along the curve. It's negative flow along the curve. So altogether, when you add up these 4 terms, what do you get when you add up a positive, a negative, and a couple of zeros? It depends on which is the negative bigger or is the positive bigger. And I point out that there's more magnitude to the vector field there. There's less magnitude to the vector field there. And so, as it would appear from the picture, there's more positive and less negative, and that adds up to positive. So there is a positive amount of circulation, boundary circulation, happening in that green square. And likewise elsewhere in this gray region. Now it's a nice little exercise to sort of think through that if I were to do the same calculation there, and you just kind of think through the four edges, pretty much the same story, different numbers, longer vectors, same result, right? So everywhere in this gray region, we get kind of the same answer, that there's a positive amount of boundary circulation happening there. Now, what happens if we do that for here, in that white region? Well, it's still a positive, a negative, and two zeros, except now the positive and the negative look like they have the same magnitude. And so we expect zero. So there's zero circulation happening there. There is zero circulation happening there. Right? Et cetera, 0, 0, 0, 0, 0, positive. Positive, positive. You can see literally where in this gray region that circulation is actually happening. Yeah?
Does it not matter when you talk about places where it's zero, does it not matter that it's outside the group box?
Oh, the gray is not that. So the region in question that we're interested in is what's inside of the purple. Right, so that whole thing is the interior. The gray is just my way of sort of highlighting for sort of explanatory purposes that's where the circulation is actually happening, because we get non-trivial circulations on those little pieces. And in the white regions, there is no circulation happening there, because when you put a little square up there, you get no circulation. Yeah, does that make sense?
Yes.
Cool. All right, now we can also quantify this, right? Now this is just kind of geometric games. It's analogous to what we did here, where I was like, hey, yeah, a lot of change happening there, not much change happening there, zero change happening there. This is the same thing, just in the context of circulation instead of change, and we can quantify it, right? If you have an explicit vector field, if you have an explicit vector field, and it's got some grand total amount of circulation. How much? Whatever. There's some sort of a total. It doesn't really matter for the purposes of this example what that total circulation is, but there's some sort of a total amount of circulation. And then if I ask, okay, well, between these 2 points, where is there more circulation happening? Well, if you want to know where the circulation is happening, you look at circulation density, aka curl. And you compute the curl. And you evaluate the curl at the 2 points in question. And if you want to know where is there more circulation happening, it's where there is the greater circulation density, right? And more is happening at the point where there is more circulation density, and therefore it's at the point 2, 4. Everybody follow it's totally analogous to the computation that we did here. If you want to know where's change happening, you look at change density. And if you want to know where circulation's happening, you look at circulation density. All right, so I think a really good exercise y'all can think through for yourselves. Again, if you want to challenge yourself on, do I really follow this reasoning? Walk through and think through the analogous reasoning concerning two-dimensional flux, right? And so I claim you can look at this picture and you can argue, for example, that on the boundary oriented as boundaries are oriented. Complete. Well, think through the 4 edges. How much outward-oriented boundary flux? Again, think it through. Think about dot products and magnitudes. And I claim you're going to come up with a positive amount of outward-oriented boundary flux here. And then where is that happening? Well, you can think through individual little squares and try to persuade yourself how much outward-oriented boundary flux do you get there? You should get 0. Think it through. Here, 0. Think it through. 0, 0, 0, not 0. Right, now again, think through those details. Look at that green square. Think about the 4 edges. Think about outward What is the outward-oriented normal vector? How does that dot with the field vector? Where is it bigger? Where is it smaller? You're going to get two zeros and a positive and a negative, and one of those is bigger than the other. All right? Think it through from the picture, and that'll tell you in some geometric sense where and how much of the purple boundary flux is actually coming from there. And likewise from, and likewise from there and there and there, etc. And again, you can quantify it, and it's this second part of this example down here. It's morally equivalent. Okay, so think through those details. I think it's a nice exercise. Okay, real quick, let's go back to the theorem. Oh gosh, it's far back here. Wow, okay, here it is. Here's the theorem. All right, let me zoom back in. Green's theorem says that, would be in highlighter mode. This is equal to that, and I deliberately glossed over an important point that we now have to come back and revisit. Very important point. There are conditions on this theorem. Conditions are important in math, right? A theorem is not just a formula. A theorem is some sort of a conclusion that happens under certain conditions, and only under those conditions. Well, the conditions here are that the vector field has to be not only continuous, not only differentiable, it has to be C1. That means continuous and differentiable, and that derivative is continuous. That's the condition that we're putting on this theorem in order for this to work. By the way, if you remove this condition or if you weaken this condition, problems at a minimum, problems come up. And very importantly, everywhere, no exceptions, not so much as a single point can break this rule, right? It's got to be defined everywhere. It's got to be continuously differentiable everywhere. No singularities. No sort of like explosions, where it's undefined in some sort of, ugly way around some point. Okay, so with that noted, let's see here. Let me go back to where we were. Whoop, too far. There we go. What goes wrong if we have a singularity? Right, again, that's a condition, right? If there's a singularity, the theorem doesn't apply. Let's see that in action, failing, right? Making the theorem not work. And here's the example. Let's look at this vector field right there. Now that vector field doesn't look like it has much wrong with it. It's so easy to write down, but it does have a denominator. If that denominator is 0, this is undefined, and in fact, I'm even more worried as I approach the origin. Not only, the numerator gets smaller, but the denominator gets even smaller, even faster. And in fact, we do have a singularity. Certainly, it fails to be defined when r is 0. So we have a problem at the origin. Green's theorem does not apply. No suggestion am I making here that Green's theorem is going to work. And in fact, Green's theorem is going to fail. Let's watch it fail. If I look around, colors. If I look around that curve, of course, is a boundary of a region on the inside. It's a boundary of that disk right there. And I can compute that line integral. And by the way, it's a healthy little exercise. You can totally compute this. I encourage you to do that. It is, you just parameterize that curve. Y'all know how to parameterize curves. You pull back through the parameterization and plug and chug, and you'll get 2 pi. Okay. But here's the thing. We also know that the curl is 0. Everywhere except at the origin. Obviously, at the origin, it's undefined, but come on, it's just a 1 point, right? The curl is 0 everywhere in the interior, except for that one little point. And if you think about how do I integrate a function that's 0, like everywhere except for the one little annoying point. But if the the integrand is 0 everywhere, it looks like this integral ought to be 0. And it is not. It is certainly not 2 pi. So Green's theorem appears to be failing, and depending on how you say it and how you define things, yeah, it fails. Everybody see what I'm talking about here? You see how so much as 1 point being a problem, and the theorem crashes and burns. All right, now there is a way to fix this. Kind of, sort of. And the details of the following are not really, well, anyway, I'm not going to talk about them in this course. I think it's a little too much. But there is a point of view that comes from the following related observation. Not only is it true that every circle centered at the origin will give an integral of 2 pi, but furthermore, any curve, however weird that curve might be, any curve that surrounds the origin, that integral will still be 2 pi, no matter what curve, as long as it surrounds the origin and oriented counterclockwise, like I've done. You'll always get 2 pi. And it is further true that any curve that does not surround the origin will give you 0. If you do surround the origin, you get 2 pi. If you don't surround the origin, you get 0. Let me say that a little bit differently. If the interior includes the origin, you get 2 pi. If the interior does not include the origin, you get 0. Now, let me just remind you, when we talk about circulation, and again, the weird ask, and I know it's strange, but it's very helpful, is that you view circulation as, it's an accumulating quantity. View it as stuff. It's kind of like a stuff. It's like a substance. Not physically, but it behaves like it's a substance. And it's a substance that accumulates over interiors. And when we're looking at an interior that contains the origin, there's a total amount of 2 pi of this stuff. And when we're looking at an interior that does not contain the origin, there's a total of 0 of the stuff. It's almost like at the origin, there's a discrete lump of stuff. Right, that would explain everything, right? That's totally consistent with the idea that surrounding the origin gives you 2 pi and not surrounding the origin gives you 0. It's like there's a lump of stuff at the origin, like a point mass, right? Except it's a point circulation. So, and this, by the way, this can be made precise after a fashion. There's a point of view on this. Again, that's a little more heavy-handed than I want to get into in this course. But if you're looking for any sort of intuition, that is a kind of a way to fix it. So anyway, the point here is that things get weird if your conditions are not satisfied, right? And certainly you can't just apply Green's theorem willy-nilly if you have a singular, even so much as 1 point of singularity. Okay, that's just kind of a cultural point. I just wanted y'all to be aware of that problem. Moving along, 6.3. Here we have another accumulation theorem. It's called the fundamental theorem of line integrals. Here it is. And you're going to notice it looks a lot like the fundamental theorem of calculus. I mean, right? That leaps off the page. F of B minus F of A screams fundamental theorem of calculus. You'll also notice that the integrand is a derivative, just like in the fundamental theorem of calculus. This is shockingly analogous to the fundamental theorem of calculus. Sure, yeah, it is. And it's just a little bit different. This applies for line integrals of vector fields instead of It's Calc 1 integrals of Calc 1 functions. But again, structurally it looks the same. Now, a quick comment on terminology. When a vector field is a gradient, some people like to call such a function conservative. There are physics reasons to do this. It has to do. How many people have had an intro physics course in mechanics, potential energy, stuff like that? Okay, all right. So, if you know about potential energy and conservation of energy, that's where the term conservative comes from. It comes from the idea that if you have a gradient, there is a way, details I'm not going to go into, to define a notion of a potential energy related to that force field, and that's what allows you to define conservation of energy. You need potential energy to define conservation of energy, and you need it to be a gradient to define potential energy. So anyway, conservative, you're going to hear that in physics classes. You'll also hear it in a lot of math classes. I feel like there's a more natural term here to describe a vector field that is a gradient. It's a gradient, right? I mean, doesn't that seem to be the low-hanging fruit, sort of the obvious, on-the-nose, seemingly most natural term? So I'm going to call them gradients. Be prepared in your future, you're going to hear them called conservative. Okay, now, I claim this is an accumulation theorem. Well, yeah, sure. In fact, the quantity that's accumulating is change. Again, I'm going to use capital delta to represent change. Pretty common choice. I hope that's relatable. And I claim it accumulates over curves. Now, this is not accumulating over areas. There are no areas in this picture, right? The accumulation is over a curve. The whole is the sum of the parts of the curve. So in particular, how much the function changes on that piece of curve and how much the function changes subsequently on that piece of curve. Hopefully no surprise. When you add those together, you get the total change. Now, my favorite metaphor for this little bit of algebra is to think about this path as being a mountain road. I'm driving along this mountain road, and the function little f that we're interested in here is altitude. Again, it's just a metaphor. This is the one I find most satisfying. And if you know how much your altitude increases on the green part of the curve, and if you know how much altitude you increase on the blue part of the curve, hopefully not a shocker that when you add up those altitude increases, you get the total altitude increase, which of course you do. And again, there's the algebra if you prefer. Okay, so it's an accumulating quantity. The whole is the sum of the parts. You can view it as being a kind of a stuff distributed over the curve. And there is an associated density. And I'm going to get to that density by first reminding you of this old formula. This might be written a little bit differently than we did back in Chapter 2, but in Chapter 2 we talked about how the gradient vector, dot product with the gradient vector, is what turns input changes into output changes, right? And the input change, when you're moving in the domain, your displacement is your input change, and then there is a corresponding change of altitude, let's say, or whatever f you're interested in. And the relationship between output change and input change, again, is dot product with the gradient. Okay, so from that, let's rewrite that a little bit. Don't forget that dr is TdS. By the way, flashback to Chapter 3. Right, section 3.2, the very beginning of in my notes anyway, very beginning of section 3.2, we talked about the dr and the t and the velocity vector and ds and various different relationships between those and other related players. Right, so make sure that you remember all that stuff. This class again is very sort of vertical. Everything builds. Right, so flashback to section 3.2 if you need to. Make sure you recall that dr is TdS. And writing it like this, we get a different way to think about this equation. I claim that I can view this as being my density, because ds is literally size, right? How big, what's the magnitude of that little displacement? How big is that little piece of road that I just drove along? We're talking about one-dimensional things. Size means length, right? So ds is the size, and this is the associated amount of stuff. So what I have highlighted in purple there is, from this point of view, stuff per unit size. That's what density is. So gradient dot T is my associated density, and with the understanding that that gradient dot T is my density, and recalling, of course, that change is an accumulating quantity, altogether, we have ourselves a theorem. And this stuff is computed as an integral, kind of casually. It sort of looks like a scalar line integral there, but it's an integral over the curve of that density. Now, of course, I know y'all remember, as we just referred to, let's see here, dr is TDS. So I tell you what, this TDS, let's rewrite it now as dr. Let's just see what happens. That gives us a different way to write this theorem. Right, this is the way I wrote it above, a vector line integral of a gradient. That's how we wrote the theorem in the first place. Kind of gives us a weird situation, though, and let me, I want to highlight this with a different color. Let me do it with this color. Oh, and you know what? Let me do it like this. Let me do that. Coming back to this point of view, aka this right here. If that is my density, a question arises, which is, okay, well, yeah, but then what is this? What is the gradient by itself? Gradient dot T is the density. What's the gradient by itself? Is there some way to think about the gradient from this point of view? I mean, I kind of prefer this notation. It's a little bit more natural, a little bit more compact. Wouldn't it be nice if I could then make some reasonable sense out of what the gradient is in this, from this angle? And there's a really nice way to think about this. It requires being a little bit flexible, so work with me here. We've been flexible in the past on this word density. Right? In middle school, density means mass specifically per unit, volume specifically, right? But we've kind of broadened our point of view. It doesn't have to be mass; it could be any sort of stuff, any sort of accumulating quantity. Even doesn't even have to be a stuff, as long as it's accumulating some sort of. I'm going to say stuff because it's easier to say. And then per unit volume. It doesn't have to be a volume. Well, any notion of size, right? So population density, for example. That's not population per unit volume. It's population per unit area. Right? Any notion of size. So stuff per unit size. We've already been flexible on that. Now I'm going to ask you to be even more flexible. We're going to broaden our point of view on density just that little bit more. What if just to make the pieces fit together, what if I think of dr as being itself a kind of a size? Its magnitude is a size. Magnitude is ds. It is literally a size, but it also has a direction. And so I'm going to call dr an oriented size. And if dr is an oriented size, I think it's kind of plausible to think of the gradient as being an oriented density. Again, I know that's weird, right? Strange point of view, but kind of satisfying in a way. It's not what you multiply by scalar size to get stuff. It's what you dot with oriented size to get stuff. Anyway, so this is a point of view. Again, you kind of don't have to, but let me just give you a little bit of a heads up what's coming let's see, when's it going to be? A couple of weeks. We're going to see another example of oriented density. This idea of oriented density you might view as being not really necessary. I understand what gradients look like. We've studied gradient. I have a good geometric intuition for what gradients look like. I'm going to stick with that one. You may be thinking, perhaps, right? Fine. The oriented density that we're going to see in a couple of weeks, you will not have a previous highly satisfying familiarity with that thing. And being able to view it as an oriented density is going to be immensely valuable in just being able to have any sort of geometric sense for what it is and why. Right? So I want you all to think of this, a little bit of a strange take on what the gradient is. I want you to think of this as a warm-up exercise, right? Kind of a segue, so that when we get to a couple of weeks from now and we find ourselves with this other oriented density, that pill will go down a little easier. Okay. All right. Okay, so again, theorem. Right? And you can view this a couple of ways. I presented it as if you want to compute change, compute it with an integral. We're going to apply it, as you might suspect, in the other order. If you want to compute an integral, we're going to compute it by f of b minus f of a. And so here's an example. This is very plug and chug, but here we go. Let me zoom. And here's the example. I want to compute that vector field. I want to compute this line integral of this vector field f over this curve C. Now, let me talk strategy for a quick second. Right? You're going to encounter questions on exams like this, and the question's just going to say, compute this line integral. And you've got a toolbox full of tools, and you've got to decide which tool should I use, right? Please do not, terrible error of judgment to just say, you know what, I'm going to pick one tool, that's how I'm going to compute things, and forget all those other tools, those are weird, I don't like them. It's not going to work. Okay, so you want to think about all the different tools and make the right choice of what is the best tool to use in that circumstance. Let's think about our options here. Now, I could pull back. The curve's already parameterized. I can totally plug and chug, pull back through the parameterization. You know, dr is r prime dt, x is cosine, y is sine, plug it in, take a deep breath, and plow. You totally do that. It's going to be inconvenient. But it's doable, but it's going to be inconvenient. And then, by side note, in other circumstances, it'll be even more inconvenient. And I'm going to call that not a very good option, frankly, in this case. Okay. Other options. Other ways that we know to compute line integrals. Let's just think about, let's rummage through our toolbox here. Geometric good fortune. Sometimes the geometry is awesome. Sometimes dot products are just obviously zero. Yeah, no, it doesn't work here. Right? No such luck. Let's see here. What else do we have? Symmetry? Ooh, no symmetry theorem. Right? Vector line integrals do not have odd symmetry. Don't even. That's a total non-starter. There is no odd symmetry theorem for vector line integrals. So no luck there. Green's theorem computes vector line integrals, doesn't it? I wonder if maybe we could use Green's theorem here. By the way, on an exam, again, I'm walking you through the thought process of how you should approach a question like this on the exam. This says compute a line integral. Green's theorem will compute line integrals in some cases. It deserves a little thought, right? A little consideration. The problem, the reason this doesn't work is that if you look at this curve C looks like that. It has a starting point, it has an ending point, right? T goes from 0 to pi. So that's what our curve looks like. And don't forget, Green's theorem strictly only applies to boundaries. And that curve is not a boundary. Yeah? Is that cool? Everybody see why Green's theorem is a non-starter? Can't use Green's theorem here. Okay, So we've considered all of our options except for our brand new tool, which is to entertain the possibility of using the fundamental theorem of line integrals. Now, to use the fundamental theorem of line integrals, keep in mind I need for my vector field to be a gradient, and furthermore, I need to be able to identify what it's the gradient of, because that's what I'm going to be using to compute on the right-hand side of the equation. So I need to know that it's a gradient, and I need to know what is the anti-gradient. Right? And I hope you all remember I like this term, anti-gradient. Some people like to call it a potential function. That's the more common term. I think it's weird. I think anti-gradient is more natural. Okay, so there's our task. I need to know if f is a gradient, and if so, of what, and boom, here it is. It is a gradient. I mean, check my algebra if you don't believe me, right? That vector field is exactly the gradient of x squared y squared, therefore x squared y squared is our anti-gradient. Is that cool? Everybody follow the algebra on that? Now, I'm gonna confess, I just did something pretty unsatisfying. I pulled that function out of a hat. I pulled it out of thin air, right? You have no idea where I got that from. There is a process. There is an algorithm that will allow you to find anti-gradients, and I'm totally going to show you that process for finding anti-gradients. I just don't want to get bogged down in details at the moment. So for the moment, I'm going to call this a magic trick. I just found the anti-gradient, right? Ta-da! And I'll show you how I did it. Let's see, possibly later today. We'll see how fast I go. How we doing? Let me pause here for a second. Anybody have any questions? Is everybody happy? As happy as you can be in a math class? Yes?
Why is C not a boundary?
Yeah, well, you just have to look at the curve itself. And so this, in particular, t going from 0 to pi, right? Now, you probably recognize this right here. That's just a unit circle, right? But that's only traces out a full unit circle if t goes from 0 to 2 pi, right? So because t goes only from 0 to pi, it sort of stops when you get there, right? So t starts at 0, that puts me here, and t stops at pi, at which point I'm here. Does that make sense? And then I just make the geometric assertion. And by the way, in situations like this where it's just screamingly obvious, yeah, that's not a boundary. You can just say that. Is that satisfying?
Yeah.
Okay, cool. Yeah. Okay, so we've got ourselves an anti-gradient, and by the way, as I just noted, you can see our starting point and our ending point by just plugging in to the parameterization. There's our A and there's our B, right? And we know that we're going to look at those points, B and A. We're going to plug those points into our anti-gradient, F. And, F of B minus F of A, boom, 0, answer. Done. Yeah? Is that cool? Isn't that better than the pullback in this case, right? If we had been doing a pullback, we would have, okay, x and y are trig functions. That means 2xy squared and 2x squared y are going to be super triggy, right? And then, by the way, dr is going to have r prime in it. That means I'm going to have even more trig in the r prime. There's going to be a lot of trig in this. And, oh my gosh. I guess we can do that, right? But it's certainly less amazingly efficient than this solution here, using the fundamental, when the fundamental theorem of line integrals applies. And again, I cannot emphasize enough, this is, going to end up being kind of obvious. The vector field has to be a gradient, and you have to know what it is a gradient of. right? So that you can't use the vector, you can't use the fundamental theorem of line integrals unless both of those things happen. It's got to be a gradient, and you have to know the anti-gradient. But when that happens, oh my gosh, for sure, 100%, totally do it this way. Forget about the plug and chug pullback. That's just tedious. This is the much better way to do something. Everybody happy? Good stuff. By the way, accumulation theorem number 4. Right? So, let's see, let's count them again. Green's theorem, two-dimensional divergence theorem, fundamental theorem of calculus, kind of a flashback, but nevertheless, totally an accumulation theorem, now fundamental theorem of line integrals. And we have a couple of big ones coming up. It's going to take us a bit to get to, but the real, arguably the most important ones still to come. Okay, a little bit of a digression, seemingly now. We'll talk about this thing called path independence. This is a really weird idea. It's a counterintuitive idea. It almost kind of feels like it shouldn't work. Kind of an outrageous suggestion, even, that such a thing would be possible. So let me start by making a seemingly obvious statement that, if you want to compute a line integral over a curve, it depends what the curve is. Well, of course it does, right? What could be more obvious? I hope that's not an outrage. You have to know the curve. If the curve didn't matter, why would we even indicate the curve, right? Of course, you have to know what the curve is. So here's the very shocking, very counterintuitive suggestion. There are some cases where most of the curve doesn't matter at all. It's weird. There are cases where only the endpoints of the curve matter. And what happens elsewhere in the middle of the curve, who cares, right? Very, very, very weird. As long as you know those endpoints, that allows you to compute the vector line integral, even not knowing what the curve is. So any two curves, C1 and C2, as long as they have those same endpoints, same starting point, same ending point, you don't need to know anything else about the curve, whatever. Any two curves, always the same, fine, cool, simple. Very weird. Okay, now, I'm going to show you some of those vector fields. And by the way, I do want to emphasize, here's something that used to confuse me personally quite a bit when I was young. This idea of path independence, that the path doesn't matter. How you get from start to end doesn't matter. Only the start and the end matter. This is a property of the vector field. Right? So, I somehow misunderstood this, and I thought it was like a property of the certain curves. I don't know. I just had my wires crossed when I was younger. So that's, by the way, why I don't care for this term right here, saying it has path-independent line integrals. It makes it look like this is a property of a line integral. I don't really think that's quite. I think it's a property of the vector field. There are certain vector fields that have this property. It's about the vector fields. So that term I have highlighted in red. It just rubs me the wrong way. So anyway, okay. Right. Okay, so let me show you again. I want to start with the obvious example of this. You shouldn't expect this to work. This idea of path independence should not work in some sense. Right? It's very surprising to think that it even would be possible, because of course, if you fix a starting point and an ending point, and you pick a couple of curves. Let's say C1 and C2. These two curves have the same start and the same end, but they're different curves. If you compute line integrals over these different curves, you should expect to get different results. Of course you should expect to get different results, for crying out loud. With the green one, you're looking at what's happening over here. With the blue one, you're looking at totally different points. Right? Why would what's happening over here have any sort of connection to what's happening over there. It seems very surprising. And again, yeah, you're going to get different answers most of the time. So with this vector field that I have here, that vector field, and I've got a couple of sample vectors drawn there for that vector field, yeah, you get different answers. And easily confirmed on that green curve, you get 0. Good little exercise. Make sure to think that through. You should be able to compute that green vector line integral, by the way, without even doing any algebra, just thinking about, okay, well, how is the fluid flowing, and is the fluid flowing along the curve? And on that green curve, it is not anywhere flowing along that curve. But if you look at the blue curve, yeah, it is. In particular, on the what you might call the second half here of that blue curve, the fluid is pretty clear. Oh gosh, wrong color. The fluid is pretty clearly flowing along the curve there, and so you get a positive, more to the point, non-zero answer. So this is a silly example. This is belaboring the obvious. Of course the curve shouldn't matter. Of course it shouldn't be good enough just to know where you start and you end. Of course you should get different answers, right? So the fact that this is so obvious and expected is why path independence is such a cool property. Because amazingly, there are cases where, yeah, pick any curve you want. It doesn't matter. It's all good. Any curve, it's all fine. And now that's what I'm going to show you. And now that we have it set up that it shouldn't be possible, all the more fascinating when it does. Okay, so here we go. The big point, the big trick that makes path independence work, if you have a gradient. By the way, it's got to be continuous. A continuous gradient field. It's going to be path independent. Check it out. Pick a starting point and an ending point. And with the start agreed upon and the end agreed upon, let's pick a couple of curves. And here's one curve. And the corresponding line integral. Here is a second curve. Corresponding line integral. Right? The idea is, I'm making the outrageous suggestion that these should be equal. And I'm going to put a couple of big question marks here. Like, how could these possibly have to be equal? And here's the beautiful thing about it. These line integrals, look at their integrand. Their integrand, f, is a gradient. If your integrand is a gradient, you can use the fundamental theorem of line integrals. If you use the fundamental theorem of line integrals, missed. You compute the green integral with the fundamental theorem of line integrals, you get f of b minus f of a. If you compute the blue integral with the fundamental theorem of line integrals, you get f of b minus f of a. You get the same expression computed only at the endpoints. They have the same starting point and the same ending point. So the green integral and the blue integral are both equal to the same thing. And if they're both equal to the same thing, they're equal to each other. And if the green and blue are always equal, no matter what curves they are, that's exactly what it means to be path independent. So not only is path independence possible, path independence is not even rare. All gradients have this property. Isn't that bonkers? I think that's one of the wildest things I've ever seen in math, honestly. I mean, from the point of view of how weird it seemed when I first saw it. I think that is just mind-blowing. All right. Okay. So, there's more. So not only is every gradient path independent, it also goes the other way. Every path independent is also a gradient. Now again, this is in the context of continuous vector fields and regularity. By the way, little regularity concerns are going to come up here and there, and it's a little annoying, and we're mostly going to sweep that under the rug. I'm going to continue to emphasize that the regularity matters, right? I don't want y'all to make catastrophic errors in your future engineering calculations because you had no idea that regularity mattered. But we're mostly going to focus on nice and regular vector fields and such. Okay. All right. So, so this goes both ways. In the category of continuous vector fields, gradients are path independent and path independent are gradients. So that's kind of wild. Okay. And by the way, if you are interested in why that is, here's a quick sketch of the proof. You can take a look if you're curious. You don't have to. It's not required. If you have any questions about this, come on down to office hours. I'll be happy to talk you through the details. Again, you don't have to, but if you're just curious, I think this is kind of a cool little argument. Okay, now here's another way to say it. It's just a different way to say it. Let me remind you what it means to be path independent. Is that if you fix a starting point and fix an ending point, then any two curves with that agreed upon starting point and agreed upon ending point will give you the same line integrals. That's what it means to be path independent, right? Path independent means that the green integral has to equal to the blue integral. Okay. Well, okay, yeah, sure, but I mean, look, saying that those two things are equal is equivalent to saying that their difference is 0, right? That's the exact same statement. I mean, no change, right? But wait a second, if I look at this difference, if I look at green minus blue, I claim we can think through green minus blue. Let's just kind of walk through following the green integral, and then, now don't forget the minus sign. We're going to walk through the green line integral, and then we're going to go backwards through the blue line integral. And if you do, I can't use purple. Sorry, hang on. I'll use dark blue. Okay, so if you do this, if you follow the green line integral and then go backwards through the blue line integral, you're effectively going around the loop like that. That is effectively its own line integral. Positively along C1 and then continuing backwards negatively along C2. So another way to say path independence, another way to say that light green equals light blue is to say that dark blue line integral is 0. In other words, another way to say path independence is to say that all closed line integrals, aka all circulations, are 0. Just a different phrasing. Is that, yeah? Uh-huh.
Wait, so is this saying that any circulation of a gradient will be 0?
Yes, absolutely. Yeah, it's a weird thing. And so let me say that's a great observation, and let me say that in just a different way. Keep in mind, circulations represent sort of a rotation of the fluid. So just rephrasing what you just pointed out, gradients can't rotate anything. There's no rotation in gradients. That's absolutely true. Yeah. So it's a pretty cool alternate point of view, different take on path independence. And let me show you one cool little application of this. I like this because I've always enjoyed this artist named M.C. Escher. I don't know if y'all are familiar with M.C. Escher, but here's an example of one of his pieces of art, and I can't remember if this is a drawing or I don't know art competently. But at a glance, this looks like some people walking, and then when you take a more careful look, you're like, hey, wait a minute. That ain't right. Right? I mean, does everybody see what's wrong with this picture, right? It's like, wait a minute, let's look at the people moving around the outside here. Like, these people moving around the outside are walking upstairs, and they keep going up and then up and then up and then and they get right back to where they were in the first place. They're always going up, and yet they always keep returning back to where they were, right? Like some sort of nightmare. Isn't that like a Greek mythology? Something? Anybody know Greek mythology? I feel like there was something like that. Anyway, doesn't make sense, right? Okay, so I like to take the point of view that this idea of path independence is a mathematical way of registering a complaint about what this drawing suggests. This drawing seems to suggest that you can go around in a closed loop where you're walking uphill the whole way and yet continue to come right back to where you had been, which of course is nonsense. And here's the way we're going to do that. We're going to think about the steepness vector field. Now, H is just altitude. H is height. Remember, the gradient of height tells you what direction is uphill and how steep is it in that uphill direction. That's flashback to chapter 2. And so I'm going to call that the steepness vector field. And it's a gradient. You can see it right there. It's literally a gradient. That's why I like the term gradient, right? And that means it's path independent, as we just discussed. And if it's path independent, that means our alternative formulation that all closed line integrals have to be 0. Now, I claim that dispenses with this Escher nonsense as follows. Let's think about what are these things that we're adding up. What is f dot dr? Each f dot dr is telling you how much altitude you gain with each step, you might say. And if those altitude gains are all positive, I overestimated my drawing speed. If those altitude gains are all positive, how could they add up to 0? So, nonsense. Everybody see that? That's just a kind of a way to put some math on the page. It's one thing to look at a piece of art and say, no, right? Here we have kind of a mathematical registering of exactly, precisely, why is this garbage? And it's garbage because of path independence, ultimately. Okay. All right. So I just think it's kind of fun. Okay. Moving along. So why do we care about path independence? Let me make the counter argument. Let me devil's advocate here. Path independence is arguably not as useful as I've suggested, because path independence is like a second screwdriver in your toolbox. If you already own a screwdriver, having a different screwdriver, you already had a screwdriver. Do you really need 2 screwdrivers? What's the point to this? And specifically, here's the idea. If you have a path independent vector field, we've already talked about, well, then it's a gradient. And if it's a gradient, you can use the fundamental theorem of line integrals. And the fundamental theorem of line integrals is awesome. Right? So from a computational point of view, if you're interested, if you're interested in computation, in most cases, this idea of path independence only addresses situations that you already know how to address. It only addresses situations where you can use the fundamental theorem of line integrals. Now, this is a little bit of an overstatement. You do, in fact, if you're going to use the fundamental theorem of line integrals, you're going to need to be able to identify what that anti-gradient is. And that is not always as easy as it is in easy examples I'm showing here in the notes. Sometimes finding the anti-gradient is a bear of a problem. And in those cases, fundamental theorem doesn't work, And if the fundamental theorem doesn't work, having that second tool in your toolbox can be very useful. So that's the purpose of my next example. The purpose of this next example is to show you how path independence can be useful without using the fundamental theorem of line integrals at all. Okay, so here we go. Let's look at this example right here. Here we have a vector field. Now I'm telling you that it's path independent. A very legitimate complaint that you might have going on in your head right now is, wait a minute, you're just telling me that it's path independent? How do we know it's path independent? When you're outside of this classroom, how are you going to know a vector field's path independent? I'm not going to follow you around and just tell you, yes, this one's path independent. No, that's not. How are you going to tell if a vector field's path independent? I've got a great answer. It's coming up in a couple of minutes. We'll see if I get to it today. Probably won't. But anyway, there is a great answer. We'll see it next week. But that is, I claim, a path independent vector field. And we want to compute this line integral. By the way, let me recognize you could probably find the anti-gradient here. Right? How would you find the anti-gradient? If you get clever, think strategically, you could probably dream it up. But let's not. Again, we want to pretend that we can't use the fundamental theorem of line integrals, so let's not think about the anti-gradient. Okay. All right, so we have a path-independent vector field. We've been asked to compute this line integral over this green curve. Because it's path independent, here's the argument I'm going to make. This is super clever. Because it's given to be path independent, I can pick any other curve that starts and ends at the same point. Because that's what path-independent vector fields do, right? Path-independent vector fields give the same answer for any other curve that starts and ends at that same point. And I can pick that one, or I can pick that one, or I can pick this one. The world is your oyster. Pick any curve you want. It's got to start and end at the same point. Pick any curve you want. The obvious choice, of course, is to make your life as simple as possible by picking that curve. Isn't that sort of clearly the most, I love straight lines, right? Because straight lines have easy parameterizations, and I like easy, right? So I'm going to pick this curve C2 instead. C2 is easy to parameterize, and on C2, which, by the way, gives me the same answer as the integral on C, and I know it does because it's given to be path independent, and these two curves have the same start and the same end, and that's perfectly legal, and this blue line integral is just easy to compute. It's just, it just rolls along, no problem. You can totally compute all those things. It all comes out of the parameterization. Boom, 0, done. Didn't have to mess around with anti-gradients, even. Didn't have to parameterize the curve. That would bring up trig. Don't have to deal with any painful trig. Just nice and easy. Is that cool? Everybody happy? Make sure to follow through these details, by the way. Right, very important, those details there. Got to make sure you can do those details. I will point out a couple of these details. Let me, because we're short on time and we don't have time for the next thing. But real quick, how do I know that this is 0? And the reason I know that's 0 is because I can see right here in the parameterization that y is always 0. I can also see it in the picture. Y is always 0. And if y is 0, then that must also be 0. So heads up for little opportunities like that. Again, every so often you get lucky with the geometry, and I guess it's, close enough. Well, I'm sure I owe you time, so we'll call it a day here. See y'all later. Have a good one. See you next week.